Hi, welcome to Integrated Science. I am Miss Sparks, and today we are going to introduce our waves behavior. So previously we have been talking about kinetic and potential energy and how the law of conservation of energy states that energy cannot be created or destroyed. And so now we're connecting it with how disturbances within particles can generate different types of waves. And that's what we're going to start with today. So we've already also talked about static electricity and the idea that the protons and the electrons are subatomic particles that can cause energy to be exchanged. And now we're going to look at it in two different types of formations in which we can observe and kind of break down what waves actually look like. And so please make sure you get out a sheet of paper and a pencil and take some notes on the things that are underlined. So we're going to start out with just talking about waves in general. So it is a repeating disturbance or movement that transfers energy through matter or space. So once again, it is a way in which energy can kind of cause a system of particles to move back and forth, back and forth, back and forth. So the ocean waves, it's just energy that is moving the water. Think about like a pond would be a great example, or a lake that maybe is a man-made one that could be in like someone's backyard or just a smaller lake. On a very calm, sunny day, there's no movement in that water. It looks pretty stagnant. But if a storm comes by that causes the particles of water to be moving, it's a disturbance. It causes the movement. Same thing with an earthquake. The earth is normally actually pretty calm for the most part. The plates are moving, but normally it's at a slow rate. But if an earthquake occurs, especially out in San Francisco at the San Andreas Fault, those plates shift very quickly and it causes a disturbance that ripples out and causes energy to move throughout those layers, which then can affect the communities that live by that fault line. And so these are all just disturbances that are moving and transferring energy through matter or space. And we'll talk about space as well in this unit, because you might remember when we talked about conduction, convection, and radiation. Radiation is the energy of movement through waves, and we talked a little bit about this word called the electromagnetic spectrum, which is frequencies that can move without any particles of matter to actually disturb, and we'll really focus in on that. So the important thing to understand with what I was just talking about with the electromagnetic spectrum is that that doesn't need a medium. And a medium is just the particles that can be disturbed when energy is moving through that system. So matter that a wave travels through is called a medium. And this can be any of our four different types of not our subatomic particles, are states of matter. So it could be a solid, a liquid, a gas, or even plasma. And we'll talk about plasma quite a bit when we get into our space unit. But the sun is made out of plasma, and it actually has sunquakes on it that scientists are able to observe this rippling effect. So it is a state of matter that we can see energy being disturbed through it. And so so I gave you the example of an earthquake or just wind moving particles of water, that is the medium. Even you hearing my voice right now is a wave in which needs a medium. My voice particles are now bouncing off of my vocal cords that are then making noises that are going to vibrate and disturb the surrounding atmosphere around me, and then it moves to your eardrum, which is a state of matter. It's a solid, and it vibrates to go to your brain to make a signal and for you to understand it. So that is a medium. It can be a solid, liquid, gas, and I didn't add it there, but plasma, because we are going to talk about that next unit. So the only type of waves that don't need a medium is called the electromagnetic waves, and these are electrically charged and magnetically charged energy sources that can travel through space. So we'll talk about what that actually looks like as we kind of get a little bit closer to that. So we're going to talk about a couple of different things. The first one is our mechanical wave. So there's two different types of waves, either a mechanical wave or a electromagnetic wave. And a mechanical wave does need a medium to travel through. So the rest of the notes today, we are going to talk about mechanical waves, how they can be disturbing different types of states of matter. So a mechanical wave is any wave that requires a medium. It's called a mechanical wave. I feel like I've said that 5 times in one little sitting here. So most all waves are mechanical. However, the other ones that are not are electromagnetic, which brings me to this slide. So our electromagnetic waves are actually oscillating electric and magnetic fields that will radiate outward at the speed of light. And so meaning that these different types of electromagnetic waves, radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays, these waves do not need any type of solid, liquid, gas, or plasma to travel through. So UV, let's just talk about that for a minute. That one's kind of familiar, is that is emitted by the sun. And so if we think about it, the space between the sun and the earth, that's just emptiness, but it's able to travel all the way from the surface of the sun to the earth, and then could possibly affect us if we are exposed too much to that radiation. And so all these different types of radiations are floating around the earth. Most of them, I shouldn't say all of them. We definitely do not want to be exposed to super large amounts of these UV, X-ray, and gamma rays due to their high frequency. That can be really, really bad for us, and we'll talk about why. But as you can see, these waves have low frequencies here, and as we move closer to the side, that frequency gets faster and faster and faster. So we'll talk a little bit about just a wave front, which is just the amount of energy that is being disturbed over a amount of time. And we're going to break it down into a couple of different terms called amplitude, frequency, wave speed, and period, which is these are parts of a wave front that help us figure out how much energy, how much kinetic energy is being moved through a system to cause those particles to be disturbed. So it carries the same amount of energy but can spread out over time. So if you think about it, you drop a rock into a pond and the ripples kind of generate out. The further and further they get away from that spot where you drop the rock, the farther and farther the ripples are away from each other. So energy is going to be really intense at the point of origin, and then as things move away, they get slower and slower and slower. So we're going to talk today also about 2 different types of waves. First one is transverse, and then we'll move into our longitudinal waves. So a transverse wave is a wave in which the particles of the medium move perpendicular to the direction of the wave traveling. So remember, perpendicular just means, like in geometry, it's like the little upside down T sign, and it just means that it's going to bob up and down. So I feel like the ocean is a great example of a transverse wave, because if you watch like a buoy or even someone that's kind of far out there, or a boat, they kind of just look like they're bobbing up and down as the waves travel past them this way. So the wave goes this way and they move slightly, but most of the part they're going up and down because that wave is going like this. And so these are called transverse waves. And so the biggest thing to kind of take away from them is that the medium moves perpendicular. Longitudinal are the other types of mechanical waves, and a longitudinal wave is a wave in which particles of the medium vibrate parallel. So think of a slinky. If I had a slinky and I was able to pull it, you'd be able to see the energy moving back and forth, back and forth, back and forth. Longitudinal waves are that, is that the medium moves parallel in the direction of movement. So it goes where in the other one, our transverse wave, it goes back and forth. They bob up and down, up and down. So the properties that we're going to talk about with a wave are slightly different in both our longitudinal and our transverse, but they still show and provide energy sources with them. So the first one is our transverse wave, and if we talk about a transverse wave, we are going to be looking at 2 different parts of it, which is our crest and our trough. Our crest is the high point, so I always think like ocean is that it's going to crest before it crashes into the shore. And the trough is that bottom part, kind of like where a cow eats out of a trough or a pig eats out of a trough. I kind of think of it that way. So crest is the high point, trough is the low point. In a longitudinal wave, those terms are called rarefaction and compression. And compression is just what it says, that's where the energy is. It's compressing the springs, or it's compressing the particles of movement, and then as it gets further away, it turns into that rarefaction, meaning that it's just spread out over time. And then we're going to be studying the wavelength is really important of how to look at how energy is moving through the system. And wavelength is measured either from a crest to a crest or from a compression to a compression. You can kind of see it here. So that was like one big compression right there. And wavelength is always measured in this little Greek symbol right here, which is lambda. Kind of feel like it's like an upside down inverted Y. But that's what we use to kind of describe wavelength. So I'm going to stop there, and then we're going to kind of get into the different points in which we're going to measure our different types of waves. Hopefully this was helpful.